Alright, welcome to the Unit 2 review video. Hopefully this will be helpful for your test either tomorrow or on Monday, depending on if you're in A or B day classes. I'm going to go through this really quickly because you can always pause or rewind the video if you didn't get something, just so I don't have to sit here for more than 30 minutes or so. First off, at the top of page 15 where your review starts, there are a bunch of words it lists. It says you need to know the definitions of. Make sure you do. Remember on our first unit test, a lot of you lost points on the true-false section because you didn't know definitions. So make sure you know them. Alright, number one, I'm using the guess method for all these problems. Number one says a pitched baseball goes 35 meters, so my distance is 35 meters, in 2.1 seconds, so my time is 2.1 seconds. It says, what is the speed of the baseball? So this is like a really easy junior high level problem, actually. Speed is equal to distance divided by time. I'm looking for speed. I do not need to rearrange. So speed is going to equal 35 meters over 2.1 seconds. When you solve for this, you're going to get 16.667 meters per second, because I took meters and divided them by seconds. Alright, number two. It says a bicycle rider rides her bike at 13 meters per second to the south. I'm labeling this as a velocity because it's giving me a direction, 13 meters per second south. It says how far will she be able to ride in 1 hour? So time is going to be 1 hour, and it's asking how far will she be able to ride. Okay, before I start trying to solve for this, you should notice a problem with this unit right here. It does not agree with this unit. So I need to convert hours to seconds. Pretty easy to do this. I'm going to multiply because I'm going to get bigger, right? I'm going to have more minutes than hours when I convert. So I'm going to multiply by 60. This will give me 60 minutes in an hour. Multiply by 60 again. This will give me 3,600 seconds in an hour. Now I can solve. V is equal to d over t. Rearrange for d. I need to multiply both sides by t. So v times t equals d. Plugging in, my velocity is 13 meters per second. My time is 3,600 seconds. So when I multiply through here, I will get an answer of 46,800 meters. Pretty easy. Alright, number three. When you read number three, you're going to see that it gives you directions, kind of like those old vector problems that we used to do. So it would be worth your time to draw these out. The first one says the man walks 300 meters to the east. And then it says he walks 700 meters to the west. So these really should be on top of each other, and that also should be a straight line, but I'm just drawing it quickly. Alright, 700 meters. And it's asking you a whole bunch of questions. First it says, calculate the man's distance. Remember, distance is a scalar, no direction. So I don't care that he went east then west. I just care that he went 300 meters then 700 meters. So I would do this to get my distance of 1,000 meters. Then it asks for displacement. Displacement does have a direction. It's a vector. So I do care that he walked east then west. To find displacement, I look at where I started, which is right here, and where I finished, which is right here. You should be able to figure out that the difference here is 400 meters. So you could write this two ways. You could say 400 meters west, or you could say negative 400 meters, because it's going to the left on your graph, into the negative x values. Lastly, it says calculate the velocity of this man. In order to do this, I'm going to use my velocity equation, which says velocity is equal to delta s over t. Delta s is displacement. So I'm going to take my displacement right here and plug it into my equation, negative 400. Now for the time values, you're going to see it gives you two time values in the problem. It says one is, I don't need that. One is 420 seconds. The other is 1,130 seconds. So what I need to do here is add these two times together, right, to get a total time. That's what goes in this equation, is total time. When I do that, I get 1,550 seconds. So when I divide through here, I get an answer of negative 0.26. I think it's 264 or something like that. I don't remember. But, or 2.25 something. Whatever. This is close enough. Remember dead baby rule. Number 4. A bug crawls in a straight line at 2.35 meters per second. This is a 5. That's a velocity 35 meters. That's a distance. How many seconds does it take for the bug to cover that distance? So I'm looking for time. Right. This is going to be this equation. Looking for t. I'm going to rearrange by multiplying both sides by t first. That cancels, so I get v times t equals d. One more step to solve for t, divide each side by v. So my equation will look like this. T is equal to d divided by v. Now I just plug in my numbers. Distance is 35. Velocity is 2.35 meters per second. So when you go through and divide this, you'll get an answer of 14.89 seconds. Pretty easy. Alright, number 5. Number 5 says the velocity of a car increases from 30 meters per second. So I know that's going to be VI. At 4.0 seconds. It's going to be a time. To 65 meters per second. That's VF. At 6 seconds. And it asks, what is the car's average acceleration? This is actually straight off of your homework. Right. If you remember here, we have a problem with having two time values. We can't use two time values, so we have to find delta t. Right, change in time, to use the equation we're going to use. So this would be 2.0 seconds, final minus initial. Now we're set up to solve. Choosing from my two equations that have VI and VF in them, this is the one I'm going to use. Because it has VI, T, VF, and A in it. Has all four of my variables. I'm solving for A, so I need to rearrange my equation for A. This is two steps. Subtract VI from both sides. So I get VF minus VI is equal to AT. One more step, divide each side by T. So acceleration equals final velocity minus initial velocity over time. Plugging in my numbers, I'm going to get 65 as VF minus 30, which is VI, divided by my delta t, which is 2.0. I get an acceleration of 17.5 meters per second squared. Remember, acceleration is the only unit that has a squared in it, so it's easy to tell if it's an acceleration. Number 6. As a car approaches a stoplight, it slows from 30 meters per second, there's a VI, to a stop. So VF is going to equal 0 meters per second at a stop. If it decelerates at a rate of 15 meters per second squared, this is also another homework problem, 15 meters per second squared. I made it negative because it's decelerating. How long will it take for the car to stop? So we're looking for time. How long will it take? So once again, I'm going to use this equation because it has all my variables in it, all four. I'm solving for t this time though. So just quickly subtract VI from both sides, then divide by t. So divide by A, sorry. T is going to equal VF minus VI over A. Plugging in my numbers, VF is 0, VI is 30. Remember, trust the equation even though it looks weird, getting a negative number up top. A is negative 15, so my time is going to equal negative 30 divided by negative 15, which is 2 seconds. Right? And it's seconds because this is in seconds. Number 7. Car accelerates uniformly from 3.0 meters per second, that's VI, with an acceleration of 5.0 meters per second squared. That's my acceleration. It does this for 10 seconds. What will its final velocity be? Once again, using the same equation, you're going to see this one a lot. Alright, finding its final velocity, I don't need to rearrange, so I just plug in. VI is 3.0, A is 5.0, T is 10. Solving, you're going to get this times that is 50, plus 3 is 53 meters per second. My units have to match these units. Number 8. Alright, so number 8, we start looking at these graphs. And I'm just going to go quickly through them. Some of these graphs, remember, we don't get a whole lot of information from acceleration versus time graphs and velocity versus time graphs. It's position versus time where we can say everything. Right? So just keep that in mind when we get to the velocity and acceleration. We won't be able to write a whole lot. So 8A looks like this, and it is a ST graph, in other words, distance versus time, position versus time. Alright, so what can we say about 8A? We can tell where it starts. It starts at the origin, because its first distance value is at the origin. Okay, this should sound familiar. It also has a positive velocity. In other words, it moves to the right because its slope is positive. Remember, slope on a distance versus time graph is velocity. Can't write. Whatever, velocity. Okay, because the slope is positive. We can also say that the velocity is constant because we have a straight line. Remember, constant slopes make a straight line. So if the velocity is constant, then the acceleration has to be 0. Remember, acceleration is change in velocity. If your velocity isn't changing, then there's no acceleration. So that's 8A. 8B. For 8B, we have a velocity time graph. And it looks like this. So what can we say about 8B based on its velocity time graph? 1, we can't say where it starts. We have to have a position time graph. So we can't say initial distance. Right? We can talk about its velocity though. So you'll see right here the velocity is some positive velocity and it stays at that positive velocity as time increases. So what we can say is this is a constant velocity because it's not pointing up or down, it's a flat line, and it's positive because it's in this part of the graph, the positive part of the graph. Since it's a constant velocity, then acceleration has to equal 0 meters per second squared. Velocity isn't changing, no acceleration. The other way you could think of this is, on a velocity time graph, the slope is equal to acceleration. The slope of this line is 0. So acceleration has to be 0. Sorry, not 9 yet. 8C. 8C looks like this. This is an acceleration time graph. Remember, we have to look at our y values. Very important. Acceleration time graph. So there's really only two things we can say here. One, we can say that the acceleration is positive and it's constant. It's positive because it's up here in this part of the graph, and it's constant because it's flat. So the other thing we can say is the velocity is changing. We can't say if it's speeding up or slowing down because we'd have to know if the velocity is positive or negative, but we can say that it's changing. That's because we do have an acceleration now. Acceleration makes velocities change. Alright, going back to page 1. Alright, we are on 8D. 8D looks like this. This is a distance time graph, and it's curved. So the very first thing that you should think of is acceleration, because it's a curved line. This object is accelerating. That's the first thing you can say. We're going to come back and give it a value in just a second, positive or negative. Let's first talk about where this object starts. It starts to the right of the origin, just barely. But it is right of the origin. It's not hitting the origin. It also moves to the right. In other words, it has a positive velocity because all of its slopes are positive. Slope is positive. Remember, slope on position time graphs is velocity. The last thing that we can say is this object is speeding up because it gets steeper as time progresses. Starts very flat and ends up being very steep. So, if our velocity is positive and we're speeding up, that means our acceleration has to be positive as well. Remember that sign convention? They have to agree in order to speed up. 8E. 8E is an acceleration time graph. This one's really easy. Your line is on the origin. Acceleration time graph. So here's what we can say. Acceleration is equal to 0 meters per second squared. Why? Because it's on the part of the graph where a equals 0. This means that the velocity is constant, since we don't have an acceleration. And that's all you can tell from this graph. Alright, moving on to 8F. Alright, 8F. This graph is a velocity time graph. This is a good one. That looks like this. A lot of things we can tell from this graph. One, we can say that the velocity is negative and it's moving to the left because it's in this part of the graph where the negative velocities are. Negative velocities point to the left. We can also say that this object is accelerating because its velocity is changing. It starts at a 0 velocity and ends up with some negative value. Velocity changes. So lastly, what we can tell is whether it's speeding up or slowing down. This object is speeding up because the velocity values increase. It goes from 0 to some negative number. Remember, the negative is just a direction, so it's not getting smaller because it's going negative. It's getting bigger because it's changing from 0. 8G. 8G is another velocity time graph. And this one looks like this. Actually, it's slid up some. There you go. Alright, what can we say about 8G? Well, we can say that the velocity is positive because it's in the positive part of the graph, and the object moves to the right because the velocity is positive. We can also say that it's accelerating because the velocity changes. Right, it's not a flat line. That would be an unchanging velocity, no acceleration. And the last thing we can say is this object is also speeding up because the velocity values increase, right? It goes from here to here. Velocity gets higher. Alright. 8H, the last graph, is a position time graph that looks like this. Alright. It's curving, so the first thing we're going to write is that the object is accelerating. Okay. We can also say that this object starts right of the origin because its first distance value is right here. Positive values right of the origin. It moves to the left because its velocity is negative and its slope is negative. Lastly, it speeds up because it gets steeper. Even though it's pointing down, it's speeding up because your slopes increase. Starts out flat, ends up steep. Right, number 9. This is something I told you need to memorize. There's a multiple choice question just like this on your test. It says the slope of a position time graph, so P versus T. This can also, you can see D versus T, distance versus time. And then lastly, you can see S versus T. That one's weird, but you do see it. This is all the same graph. Position versus time, distance versus time. The slope of the graph is equal to the object's velocity. Need to know that. Right. And then it also says, well, the slope of a velocity time graph, velocity versus time, the slope of this graph is going to be the object's acceleration. That's how we made all those graphs in class. That's how we analyze graphs. You need to know both of those. Number 10, you got two graphs. One looks like this. The other one looks like this. And they're both position versus time, distance versus time, whatever you want to think of. And I asked, what's the difference between these two graphs? Well, first off, they basically start at the same place, so that's not the difference. They're both moving to the right because they have positive slopes. That's not the difference. The difference is this slope over here is bigger than this slope because the line's steeper. So what we can say is, whatever this object is, let's say this is graph 2. So object 2 is moving faster than the first one. Moving faster than number 1. In other words, the velocity of graph 2 has to be bigger than the velocity of graph 1 because the slopes are your velocity. Number 11. Draw a position time graph for a ball that speeds up in the negative direction. Right, this is a little tricky because we've been working the other way so far. So this speeds up in the negative direction. Right, and it's a position time graph. Right, so in order for our object to move in the negative direction, it has to point like that. Remember, we have to have negative slopes. So wherever I draw it, it has to point down. Otherwise, I'm not going to get an object moving to the left in the negative direction. So really all I have to determine is, if I start up here, if I start up here, do I curve this way to speed up, or do I curve this way? And obviously it's the first way, because that's the one that gets steeper. Let me delete some of these dotted lines. So this is an object speeding up in the negative direction. You could have drawn this anywhere. You could have drawn it here. You could have drawn it at the origin. You could have drawn it in the negative part of the graph. It doesn't matter. As long as it's pointing down and getting steeper, then you're moving in the negative direction and speeding up. All the same thing. Alright, number 12. Draw a velocity time graph for an object that is speeding up in the negative direction. So it's the same sort of situation, speeding up in the negative direction, but now I have a velocity time graph. So let's think about what this is going to look like. In order to speed up in the negative direction, I have to be in this part of the graph. This is where I have negative velocities. This is where I'm moving to the left. Up here I have positive velocities moving to the right, so I can't draw anything up here. That's going to be incorrect. It has to be down in this part of the graph. Right? It needs to speed up. So I have two options. One, I can draw a line that looks like, goes from here to here and looks like this. Or I can draw a line that looks like, that goes from here to here and looks like this. The solid line is one that's speeding up because its velocity is small here and it's bigger here. Right? Remember, the negatives are just directions. So the answer to this one's going to look like this. This would be a velocity speeding up in the negative direction. Right, number 13 is one that I'm sure plenty of you got stuck on. You're given a graph that looks like this. It's a velocity time graph. Here we go. You have a flat line first, and then it points downwards, and it gives you some values. It says this is 25 meters per second, right here. And then it says at 4 seconds is where that change occurs, and then the whole thing is 8 seconds long. Right, this is v, velocity, and this is time. So part A says, what is the object's displacement during the first 4 seconds? So we're looking for this at t equals 4. Change in s is displacement. So a lot of you would have gotten stuck on this problem because you forgot about this definition. We said the area underneath the curve of a velocity time graph gives me displacement. So if I find the area of this rectangle, I will get the displacement at 4 seconds. So really what I have, if I redraw my shape, I have a rectangle. The width is 4 seconds. The length is 25 meters per second. So in order to get my delta S, I'm going to say L times W. So this is going to equal 25 times 4. This is 100 meters. That's part A. Part B says, what is the object's total displacement? So we're looking for delta S over the whole time, which is 8 seconds. Two ways you could do that. Well, really there's only one way. Alright, what I have to do to find the total displacement is now find the area here and add it to the one I just found. So I have a triangle. The height is easy to find, 25 meters per second still. The base, sometimes students mess this up. This is not 8 seconds long. The whole thing's 8 seconds long. This right here is only 4 seconds. If the total is 8, the first part's 4, then the second part has to be 4. So to find delta S, I'm going to use the area for a triangle, 1/2 base times height. This is going to be 1/2. Base is 4 seconds, height is 25 meters per second. 25 times 4 is 100, divided by 2 is 50 meters. So my total displacement would be 100 plus 50, which is 150 meters. Alright. Almost done. Number 14 says, draw an acceleration time graph that shows an object's acceleration as it changes from blah, 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 blah. Number 14, I don't know why this is on your review. Do not worry about it. Omit it. You don't need to know this. We never deal with acceleration that changes, so there's no reason for you to draw a graph. Alright, number 15 is similar to number 13. It says, using the graph below, calculate the object's total displacement. Now, by the way, if you're ever calculating displacement from a graph, it's always going to look like this. So this graph looks like this. You have 0 seconds here, 6 seconds here, and then it says you have 10 meters per second at the top. So once again, to find displacement at 6 seconds, I'm finding this area right here. So delta S is going to equal 1/2 base times height. I have a triangle. 1/2. My base is 6 seconds long, and my height is 10 meters per second long. Right, 6 seconds, 10 meters per second. So 1/2 of 60, 6 times 10 is 60. 1/2 of 60 is 30, and it's displacement, so it's going to be meters. Very simple. Alright, that concludes the review video. There's one more thing I'm going to cover in class, which is calculating slope. So that might be something you want to look at tonight, how to calculate slope. The equation that I'm going to teach you is y2 minus y1 over x2 minus x1. Something you've seen before. Review that, look it up online, or if your math book has the slope equation in it, you can look at it there. It's something very easy, but you need to know how to do it for your test. Don't forget to study definitions. Look through all your notes. Just read through them. Just once is fine. Read through all your notes. You will get the equations on the test, so you don't need to memorize them. And get some rest. Be prepared for your test tomorrow if you're in A-Day, and Monday if you're in one of my B-Day classes. See you later.